Hey everyone, welcome back to the channel. I'm Vaibhav, and so far we've built some pretty solid linear regression models. But here's the million-dollar question. How do we actually know if these models are any good? This is a very important topic in machine learning, so this video might be a little longer than what you've seen so far. Today we're going to learn how to properly measure model performance and deal with the messy challenges that real-world data throws at us. If you're following along with this series, hitting that subscribe button really helps us create more content like this. So, what makes a model good versus bad? Well, we can't just eyeball it, we need solid numbers to back up our claims. Let me show you what I mean using our trusty 8-car dataset. Here's what our model predicted versus what actually happened in the market. Now let's turn these errors into meaningful metrics that actually tell us something useful. First up is mean absolute error, or MAE for short. This one's straightforward. Just take all your errors, ignore whether they're positive or negative, and average them out. When should you use MAE? It's perfect when all errors matter equally to your business. Like if you're a car dealer and being off by $200 or $2,000, both just cost you the same amount in customer trust. Next we have root mean squared error, RMSE. This one punishes big mistakes way more than small ones because it squares the errors first. Our RMSE is about $316. RMSE is your go-to when large errors are really bad for your business. Think about it. If you're pricing insurance and you underestimate risk by a huge amount, that could bankrupt you. Small errors, not so much. Then there's mean squared error, MSE. It's just RMSE before taking the square root, so it's in squared units. Honestly, MSE is mainly used for mathematical convenience during model training. For actually understanding your model's performance, stick with RMSE since it's in the same units as your target variable. But the real star of the show is R squared. This tells you what percentage of the price variation your model actually explains. If you get 0.95, that means you're explaining 95% of why prices differ. That's pretty impressive. Now here's where things get interesting. Regular R squared has a sneaky problem. It always goes up when you add more features, even if those features are complete garbage. That's where adjusted R squared comes in clutch. It actually penalizes you for adding useless features. So if your regular R squared is 0.95, but your adjusted R squared drops to 0.88, that's telling you some of your features might not be pulling their weight. But here's the thing that catches everyone off guard. All these beautiful metrics we just calculated, they only tell you how well your model fits the data it was trained on. The real question is, how well does it handle completely new cars it's never seen before? This is where overfitting becomes your worst nightmare. Your model basically memorizes the training data instead of learning the actual patterns. It's like that student who memorizes all the practice problems but completely bombs the actual test. Here's how we fix this. Instead of using all your data for training, you split it up strategically. About 60% goes to training, 20% to validation for tuning your model, and 20% you lock away for final testing. That test set doesn't get touched until you're completely done building your model. Now let's talk about the real-world headaches that will definitely mess with your models. First headache, outliers. Imagine finding a 3-year-old Honda that somehow sold for $35,000 when everything else goes for $20,000. Maybe it belonged to a celebrity or has some crazy modification. These outliers can completely throw off your model's understanding of normal pricing patterns. Second headache, missing data. Real data sets are messy. You'll have cars with no mileage recorded, missing brand information, or incomplete maintenance histories. You can't just ignore these, you need a strategy. Third headache, when your features are too similar to each other. Like if you include both car age and years since manufacture, they are basically the same thing. This makes your model confused about which feature is actually doing the work. Fourth headache, when relationships aren't actually straight lines. Maybe luxury cars hold their value differently than economy cars, or depreciation speeds up dramatically after 10 years. Linear regression assumes everything's a straight line, which isn't always reality. So how do you deal with all this mess? For outliers, use statistical tests to spot them, then decide if they're errors to fix or genuine rare cases to keep. For missing data, you can either toss incomplete records or fill in reasonable estimates based on similar cars. For redundant features, check correlation matrices and remove the ones that are basically duplicates. For nonlinear patterns, try transforming your data or consider that maybe linear regression just isn't the right tool for this job. Here's the bottom line. Clean, well-understood data with a simple model will almost always beat messy data with the fancy algorithm. Spend your time getting to know your data really well before you worry about complex modeling techniques. Up next, we're diving into linear regression assumptions, basically the fine print that tells you when linear regression will work and when it'll completely fail you. If this breakdown of model evaluation made sense, that subscribe button helps us keep making content like this. Drop a comment and tell me, what's the messiest data problem you've run into? Thanks for sticking with me, and I'll see you in the next video where we tackle those crucial assumptions.